Okay, let's start. All right, carboxylic acids. What you're meant to know. Identify the aldehyde or primary alcohol from which a carboxylic acid could be produced by oxidation given its structural formula. So very similar, backtracking what reactant was used to produce a carboxylic acid. Next, write an equation for the ionization of carboxylic acid in water. So carboxylic acid being an acid, it can dissolve, well, depending on how many carbons are involved. Thirdly, write the equations for the reactions of carboxylic acids with hydroxides, carbonates, and hydrogen carbonates, and describe changes that accompany these reactions. Again, it's an acid, so it can react as acid, act as acid, and react with bases. Finally, explain why some drugs with carboxyl groups are usually taken in a form of their salt. So a bit of biochemistry or medicine, medicinal chemistry, starting from here. All right, preparation of carboxylic acids. How can you prepare carboxylic acids? Firstly, preparation. What can you do again? What reactant can you use again? Oh, yes, yes. Yeah. Let's just use RCOH. Probably do it this way. So that's just primary alcohol. And you can do it, yep, acidified dichromate solution. And there are two products from that. It's going to be aldehyde. Same reagent. So if you manage to keep that reactant inside of a chamber, it can become carboxylic acid, yeah? Okay. So what kind of equipment and setup should be used? What's the reason why as well? I just mentioned something. Aldehyde here, if you remember that, it evaporates, it boils off really quickly because boiling point of aldehyde is much lower, even compared to alcohol, or well, definitely much lower than carboxylic acid. You remember physical property that we were talking about in the second subchapter? Yeah, subchapter. If it doesn't contain OH hydroxyl group, hydrogen bonding won't be present, so that would boil off fairly quickly. But if you are trying to create carboxylic acid, you want to keep that earlier. So what you have to use, equipment that you have to use would be firstly reflux setup. In a slight white space, you can draw a diagram even. So what you can have is a pear-shaped flask and reactant product mixture in it. You heat it up. And when you heat it up, what's going to happen is the mixture trying to evaporate from that. Yeah. But if you had water, sorry, I should have put water going in and coming out into, remember what this equipment part called? Did I mention that just then? Probably not. The pear-shaped flask, and this is condenser. Basically what it does is it cools down the liquid that boiled off, condenses it back, and that trickles down back to here. Okay, so you will be able to probably see even a vapor line going up and down. Okay, because this setup doesn't allow anything to evaporate, you can keep all the reactants. So you can keep cooking, okay, without letting anything escape. All right. If you have some aldehyde, they will try to evaporate. So yeah, reflux is needed. Okay. So why do we use reflux equipment in your own words? To prevent reactants or products from evaporating or being lost. And by keeping all the reactants and products, what you can also achieve is to be able to keep cooking the reactants for longer period of time. Okay. Because all the reactions, not all, sorry, some reactions take a lot of time for the reactants to bump each other and have successful collision and form products. Yeah. Now imagine cooking a potato. It doesn't happen within 1 minute, right? You have to cook it a bit longer. Same for some reactants. Okay. If you want to achieve as much of the yield of the product, you would have to keep cooking or heating up as long as you can. Okay. So, yeah, so the third point there. Can you give the names and right structure formula of alcohols from which following carboxylic acid could be produced? If you had something like this one, by the way, what's the name of this alcohol? Sorry, carboxylic acid. How many carbons are in the chain? 4. Okay. Good. So what's the name of this carboxylic acid? Butanoic acid, and that's it. Okay. For you to make butanoic acid, what sort of aldehyde would you need? What sort of aldehyde would you need? So don't mess with carbon chain. You can keep that. Right? So you will have just 4 carbons again. But instead of oic acid, you just change the ending really for this case. Butanal. Yeah. For you to make butanal or butanoic acid, what alcohol was used? Do we still have 4 carbons? Yes, you should. Needs to be primary as well. And you still have 4 carbons. So you don't change anything that's within the carbon chain, right? But you will change the ending, right? Carboxylic acid, that's aldehyde. Instead of CO double bond, you have to have a single bond to oxygen from here, right? Yep. How many hydrogens should this carbon have, this end carbon? The carbon is bonded to this carbon, as well as OH. Yeah, can bond to the hydrogen. Can just write it as CH2 and OH. What's the name of this alcohol? Very close.
Butane
1O. Yeah. With butanol, you have to specify where the OH group is attached to, because butane 1O, butane 2O, they're different things. Yeah. Good. Something that you probably didn't need to know would have been, but something that you've also used in the past. Is this. Now, you might not need to name this one, but you should be able to draw the structure of alcohol which was used. Okay? Now, this is called benzoic acid. What alcohol was used to you reckon? Well, you don't need to be able to name, but hopefully you can draw. A benzene ring. Work with the carbon that's there. Okay, you can't get rid of carbon. So if you just draw OH like so, that would be wrong. Yeah. Keep the carbon there. But this carbon now has OH group attached to it instead. Okay. Now what's not drawn or written is hydrogens, because I use skeletal formula, which you don't have to write hydrogen. But remember, there are hydrogens that's not written. Yeah, around every carbon. Okay. Moving on. Okay, so weak acids only partially ionize in water. What are we talking about? Well, it's still carboxylic acid. Now, back in term 1, you guys did volumetric analysis. And remember what carboxylic acid you used or you tried to look for in vinegar? Good, ethanoic acid. Okay, so that was carboxylic acid. Do you remember that that was considered as weak acid? Good. So ethanoic acid was weak acid. In fact, carboxylic acids, they're considered to be all weak acids. All right. If it only partially ionizes in water, okay, what sort of thing do you need to know again? I'll change the question. What sort of arrow should you use to indicate that acid is weak? Good, good. If an acid only partially ionizes, you have to use two-way arrow. So for example, let's use ethanoic acid as its example. So you've got carbon. Let's just draw it out. So 2 carbons, so that's F, ethanoic acid. Now in water, it would be partially ionized, okay? Some would be still staying as carboxylic acid, but some would be donating proton to water, okay? Oxygen is minus, so that's permanent charge. Or if you are letting this with, react with water, you might be drawing as because in solution, this is really what's happening. So this hydrogen could be donated to water. It really means the same though. Do you remember what this ion is called? Good, hydronium ion. Yeah, hydrogen ion, hydronium ion. This is a lot more, I guess, realistic representation. Because solution is made with acid and water. Yeah, it's very hard to get 100% of acid like this one. So, all right. Now, because it's a weak acid, it can react with bases to form water and ionic carboxylate salts. So remember the term salts. It's just ionic compound. Yeah, that's dissolved in water. Okay. Now there are a few things that you can let the acid react with. Firstly, what was it? Any base. Secondly, carbonate. Thirdly, hydrogen carbonate. The reaction with base. Any generic one's fine. R, C, or H plus or H minus. What do you think would happen? R, C, or H plus any carbonate. What's going to happen? R, C, or H plus HCO3 minus. what's going to happen. Good. Yep. Every time you see carbonate and acid reacting, you need to think of carbon dioxide formed. That's one of the patterns that you should really memorize. Okay. So if it's just acid and base, you should really get salt and water. Yeah. Salt being what? Well, R, C, O, O. And depending on what this OH group was attached to, like if it was sodium hydroxide, sodium would be attached to that. Sodium ion would be attached to that. Yeah. Now, I didn't write it down because that's just a, what sort of ion is it? Something that you can omit from each side. Something that's not really part of the reaction. What do you call those ions again? We'll come back to that. CO3, 2 minus, calcium carbonate, so something that makes up eggshells, seashells, some of the buildings, yeah, limestone. Again, you will get some sort of salt. If it was bonded to calcium, you could make calcium ethanolate. Yeah. But in this case, what you will also get is CO2 gas and H2O. Now, because this is gas, you would see some sort of bubbling happening. Okay. Cookie chemistry as well. You might be putting sodium bicarb. That's a baking powder, I'm pretty sure. If that reacts with some sort of acid within the cookie, then you could be observing bubbling up. As the reaction goes, it makes the air pockets in cookies and pancakes, that becomes fluffier. Bread, same thing. Sourdough, they all become fluffier. All right. The products will be very similar. You'd probably have to do a bit of balancing here, right? One hydrogen, two hydrogen, one hydrogen taken, so that's balanced here. One hydrogen only, the two here. I might just put two in front here. On the lecture note, it says effervescence is observed with CO3 2 minus and HCO3 minus. So effervescence being bubbling, okay, carbon dioxide coming up generated due to the reaction. If you have had Veroca, those tablets, you put in water, you start, bubbling up. That's effervescence. Okay. Yeah, you need to be able to write these equations with any given acid, with given any base or any carbonate or hydrogen carbonate. Okay. Because depending on the question, they might give you calcium hydroxide instead of sodium hydroxide. Yeah. So make sure you can balance that. The carboxylic acid functional group is, what was I going to learn? Oh yeah, solubility of carboxylate salt. Yeah, so let's talk about that. What do you think? The functional group itself, when it comes to solubility, what can you say about COOH group? Soluble because it's polar. Good. So group is polar. That's one thing. So solubility wise, what do you expect? High solubility. Yeah. Yeah. So has high solubility due to polar OH group. What's the condition now? If you remember the physical property part, we talked about this rule. If there were more than 6 carbon, whatever functional group that is there, it's going to be still soluble. Yeah. So what's the condition? Carboxylic acid is soluble because of OH group, but only when what? Yep. Correct. So carbon chain less than 6. Now, this is only for carboxylic acid. If you, though, could make carboxylic acid into carboxylate ions, which you could achieve by letting acid and base sort of reaction happen. Okay. So all these carboxylate ions, whether that's bonded to calcium or sodium, right? They would be soluble. Why? So we are talking about solubility to water, right? So diagram. RCOO minus. It's a carboxylate ion, isn't it? Yeah. Now you can dissolve it into water, we said. What would be happening in between here? Ooh, very close. Ion and good. So if the salt was created, okay, it will have negatively charged oxygen part. Yeah. Now that side can interact with partially positively charged hydrogen in water. But this is dipole. What's this interaction called again? Ion dipole interaction. So draw that diagram there. Now, because the oxygen is going to be permanently negatively charged, okay, this interaction with water is very strong compared to carboxylic acid itself. It's so strong that it kind of overcomes the limitation of carbon chain length. Yeah, we just said the carboxylic acid would not be soluble if there were more than 6 carbon. But if they were made into salt, they can dissolve into water. Okay? Few more slides. Now, that's a good property if you're trying to make some sort of medicine. Now, what you can find on that lecture note is aspirin on the left and ibuprofen on the right. And you can see that they both have got more than 6 carbon. There's a benzene ring in between as well. So there are more than 6 carbon within the longest carbon chain. So normally they wouldn't dissolve. Yeah, they're insoluble in water. Why? Well, I just said that, didn't I? There are more than 6 carbon. They're both solids at room temperature, but in tablet form, they usually mix with solid sodium hydrogen carbonate. So when you take it as tablet, they come with some sort of base within it too. Okay. Aspirin tablets. Year 10 students a few days ago, they looked at how fast it would dissolve depending on the temperature. You know, simple prac, but they could see that effervescence is happening when aspirin was put into water, and as the temperature goes up, it dissolves faster. Couple more slides. When mixed with water, the carboxylic acid is converted to water-soluble carboxylate form. Because there's sodium hydrogen carbonate, the sodium will be interacting ionically bonded to carboxylate ion. Yeah. When it happens, an effervescence of carbon dioxide accompanies the dissolving process. Why and how is this good? Why do you need to dissolve that, or why do you need to make carboxylic acid to salt form? Think of it, aspirin, ibuprofen, they are both medicine. They need to be broken down and probably absorbed by body faster, yeah? Water insoluble, water soluble form, which one will be the best option if you want to, if your body needs to absorb that? Water soluble. So what would you want to have? Carboxylic acid form or carboxylate ion form? Yeah, needs to be in ionic form, yeah? So there we go. Can you write that? So if as the carboxylate salt, the drug is easier to administer. And it would act fast. And I took that out from essentials, so yeah. So in ionic form or carboxylate salt form, the drug is easier to administer. And it would be faster acting. After a while, when the effervescence is all done, carboxylate ion, they react with hydrochloric acid, stomach acid, and it's converted back to carboxylic acid. So yeah, it also needs to be, I guess, protected by having a bit of base in your stomach. Otherwise, absorbing doesn't happen. It would go back to insoluble form quickly. Yeah. So you do need to have a bit of base to go with when you take those tablets. Okay, let's do some questions regarding that. And yeah, after 5 minutes or so, we'll start looking at chapter 3, topic 3 questions for revision.